do announcements first. We have homework 2 due tomorrow, right? So I have office hours after class today if you want to chat about that. I neglected to announce in class that Umair has modified his office hours. We posted on the Blackboard site, but I didn't say it in class. So let me say it in class right now. So Umair's office hours are now Monday. So now Monday 4 to 5. And Friday 11 to noon. That's after the recitation. So he has 1 hour. So he moved the Wednesday hour to be the one after the recitation because there was more student demand for help after the recitation than on Wednesday. And we still have some early in the week in case you want to get a head start on the homework or whatnot. So yeah, that's pretty much it. Recitation tomorrow. Umair is going to work some map and ML problems. I guess maybe finishing the problem that he started last time but didn't finish, and then various matrix exercises, so circulant matrices, symmetric matrices, Toeplitz matrices, which we'll talk about today, and how they relate, and these kinds of results, and how to think about them, and so on. So practice for that. Any questions? Are we good? Okay, so I'll keep handing these out. No one has actually used them yet, but I'm waiting for some brave person. You don't have to actually wait until I'm speaking too fast. You can just kind of randomly throw this up if you want to remind me to speak slower, or I usually give one to the camera person as well. So if you find I'm speaking too fast or I'm writing not hard enough so it doesn't pick up because of low contrast, just hold up the sign and then, yeah. Okay. So today I'm hoping to finish the signals and systems background, and then beginning next week we can talk about modeling our CommCloud channel, and then from there how to communicate over it. You have lab 2 out. That's the last of the analysis labs. Starting with lab 3, we're going to start doing design, communication system design. Okay, so we're kind of emerging from the the background part of the class into stuff that's more interesting. The background section kind of ends with a bit of a doozy, however. So this last lecture, it's a really important lecture. We introduced the cyclic prefix and postfix in this lecture. Those are really important concepts for us. Okay, that's like the basis of OFDM. Those concepts, though, are a bit technical. The derivations are just kind of intricate. So I plan to go slower during this lecture than most lectures. According to my lecture schedule, I'm going to cover material at half the pace that I usually do in this class in terms of like how many notes I cover, per hour. So I intend to go kind of slowly, but feel free, as always, to stop me, ask me to go back, ask me to slow down if it's not clear. I don't think any of the ideas that we cover in this lecture are especially subtle, okay, but there's like a lot of indexing. You'll see what I'm talking about. There's a lot of indexing and just kind of intricate math to keep track of. But it's important, okay? I wouldn't subject us all to this, okay, if we weren't going to use the ideas in a really critical way later. Okay, so let's recap where we were. So we're doing kind of like, the whole signals and systems story, but in a finite length version, like a finite length version of it, finite time horizon version. Okay, so we define the DFT as just a matrix multiplication. It's a unitary matrix. We wanted to express circular convolution as a matrix multiplication, and we do that with what are called circulant matrices. Okay, so we call it matrix circulant. It can be written in this way. So you have the left column, which can just sort of be arbitrary. And then each subsequent column is just like a downward circular rotation of the previous one. Okay, and you get all n different circular rotations. And if you were to do the next n plus first column, you get the leftmost column back again. Okay, so it's a square n by n matrix. Has like n degrees of freedom, if you will. Once you determine this leftmost column, everything else is determined once you know it's circulant. Okay, so we noted that multiplying a vector times a circulant matrix is basically doing a circular convolution. And the thing you're convolving with, we call the impulse response of the matrix, or the vector associated with the matrix. And you can motivate the impulse response terminology a couple of ways. One is to view this as a system, and then like viewing x or passing x through the system is like convolving x with must be the impulse response of the system, right? That's one way of looking at it. The other way is to say, well, you know, if you write Cx like this, so C times x would look like that, right? So if we choose x to be an impulse, i.e. 1, 0, 0, 0, 0, 0, like that, okay, when you multiply it out, you're just going to pick off this leftmost column, right? So if I feed in an impulse, then that's what I get out, so impulse response. Okay, so circular matrices have a lot of structure. As such, they can be diagonalized by the DFT matrix. Okay, so this was like the main theorem from last time. I said this is probably the most important theorem in the class. It's the theorem we'll do today is probably like the second most important. This is probably the most important one. So I showed you a couple ways of thinking about this result. One is that it's doing like an eigenvector eigenvalue decomposition of a circulant matrix. So these are the columns of W are the eigenvectors, and the diagonal entries of lambda are the eigenvalues. You can think about it that way. Alternatively, I said you can just multiply both sides of this by some arbitrary vector x, like that, okay? And then you can read this equation, you know, two ways. The left-hand side says that take x, convolve it with the impulse response. Okay, that's equivalent to, the content of the theorem is that's equivalent to taking x, converting to the frequency domain, multiplying by the DFT of the impulse response, scaled, and then convert back to the time domain. Okay, so it's basically saying that the DFT here turns circular convolution into just like pointwise multiplication, right? Okay, so that's a really neat story. I mean, it's very clean mathematically. It's not necessarily very useful for us though, because this all kind of hinges on the operation of interest being circular convolution, right? And I pointed out it like, you know, real world systems don't really do circular convolution, right? It's not a naturally occurring phenomenon. Okay, it's mathematically very elegant, okay, but it doesn't tend to happen out in the real world. Regular convolution happens all the time. You know, any LTI system you can think of conceptually just like running one big convolution continuously, okay? In particular, the COM cloud, you can think of as running a regular convolution, you know, continuously. We'll talk about that next week when we model the COM cloud. But that's regular convolution. That's not circular convolution, right? So in order to apply this theory, we need a way of applying it to regular convolution, okay? So that's what today's lecture is about, okay? Basically, how do you take a result like this and use it to say something about regular convolution? Because it's saying something right now about circular convolution, and it's not so useful for us, okay? All right, so to bridge the gap from circular convolution to regular convolution, we'll first put regular convolution in matrix form. Okay, so I want to write, you know, doing circular convolution is like multiplying by a circulant matrix. So then doing regular convolution is like multiplying by what? Okay, we need to answer that question first, and then we can talk about how to bridge the gap from this result to regular convolution. Okay, so here's the big thought experiment we laid out last time. It's sort of notationally intensive, okay, but I think it's actually a very natural setup to consider, okay? So suppose you had a vector of samples. Think of this as like the wave file you send into the COM cloud, okay? So it's just a vector of audio samples, right? Okay, suppose you take that and that vector and just zero pad it. So just put zeros forever on either side. You get a two-sided infinite in duration discrete time signal, right? So this discrete time signal is, you know, equal to these values over the time range 0 to n minus 1, and then it's just equal to 0 outside of that window, okay? Likewise, I'll call that my input. Okay, likewise, I can take an impulse response vector, okay, which I kind of index in a non-standard way here, right? And starting with 0, I start with minus n minus, and then we increase up to 0 up to n plus. Okay, so some vector. We can likewise zero pad this thing to get a doubly infinite signal h. Imagine now we're just doing a regular convolution between x and h. These are both like doubly infinite discrete time signals, so this is, you know, an operation we hopefully know quite well. All right, and then once I've got the output of the system, I window it. Okay, so I retain all the samples from 0 to n minus 1. Just discard the other ones, throw them out. Okay, take these n samples, pack them into a vector like this, call that y. All right? So the story to have in your head is, you know, this is like the impulse response of the COM cloud. This is the wave file that you send in. Okay, and when you play it, you implicitly you kind of have silence on either end of it. Okay, the ComCloud, as we'll talk about next week, is basically doing a discrete time convolution plus adding noise, which we're ignoring right here. Okay, and then the ComCloud software, of course, it doesn't give you like a doubly infinite signal, right? It truncates it, and you get a vector. You get a wave file output. Here's your wave file output right here. Okay, so we understand mathematically how does this vector map to this vector here. Okay, so think of h as being fixed. That's like the system impulse response. Okay, I'm choosing x. Okay, I can choose x however I want. I want to understand how this vector gets mapped to this one. Okay, h. As we noted last time, it's got to be linear. Okay, because like going from here to here is linear, and then this is linear if h is fixed, and the windowing is linear. Okay, so x to y is linear, so it's got to be a matrix. It's got to be expressible as a matrix. The question is, what is the matrix? Thank you. Okay, so we wrote down the convolution sum and just sort of reasoned through what the matrix would have to be. Okay, so if you look at y0, that's a sum of all the x samples with different weights. And we reasoned through what the weights had to be in each of these components just by staring at the convolution sum. And this is the matrix that we got. Okay? I think we ended right here on Tuesday. Yeah? Any questions on this? Yeah?
How come we choose to window y to have the same length as x?
Good question. You don't have to necessarily. I mean, I could define another thought experiment where you kind of go before and after. I guess the best answer to that is like ultimately I'm going to. It's sort of an argument of convenience, really. Like I'd like to apply a result like this in the end. Okay, so I'm going to jump ahead a little bit here. Okay, so ultimately we're going to try to communicate over a system like this. I'm going to try to encode bits into an x, and that's going to go through the channel, and the receiver is going to get a y, and it's going to try to extract the bits from the y. Okay, that's what this class is all about in the end. Okay. Turns out if the matrix that you get, if the mapping from x to y was diagonal, then life is a lot easier. Okay, because I can encode some bits in one sample, some bits in the next sample, and so on. And these bits don't intermingle with each other if the matrix is diagonal, right? They just pass through without interacting. Okay, that's called ISI, intersymbol interference. We'll talk about it a lot later. Okay, I'm giving a sneak preview here, but it's nice to have a matrix kind of governing your x to y that's diagonal, but in reality they're usually not. Okay, ComCloud not for sure for reasons we'll talk about next week. So I'm going to use a sort of result like this to try to diagonalize it. Okay, use transforms to try to turn it into a different channel that looks diagonal, and these diagonalization results always use square matrices.
So since like a convolution is going to end up as a longer signal, we lose some information at the
yes.
For the sake of convenience.
Yes,
okay.
Exactly. You are throwing away information, yeah, because the convolution, yeah, y would have like a longer duration than x, and we're going to kind of chop off the front end and the back end of y just so that we can sort of apply these sorts of results. And if you had a result like this that's had like non-diagonal c, then you can kind of retain that information and potentially do better performance-wise, but it ends up being like a lot more complicated. Other questions? Okay. So let's talk about that matrix. Okay, that matrix is not circulant in general. We noted that last time. It does have a certain structure to it though, right? So let's call this H, that matrix, H. All right, now if you look at H, let me grab the full rainbow here. Okay, if you look at H, the diagonal entries are all the same, right? They're H0 all the way down, right? The super diagonal, as they call it, like the diagonal shifted up, those are all the same too. It's all H of -1 all the way down, right? So it's like you have h of minus 1 copied all the way down. Here you have h of 1, and so on. Right out of colors, we can do white, I guess, like that. That's the structure it has, right? So along each of these diagonals, if you will, the matrix is constant. Anybody know what we call a matrix with that structure? Sorry? Diagonal matrix is one for which everything off the diagonal is 0. So the diagonal entries don't have to be the same. Like, I would call that a diagonal matrix, but these are different. So the requirement here is that, like, you know, along this diagonal they're all the same. And then these don't have to be 0, but they all have to be the same. It's just a, you know, jargon thing. I actually said the word earlier during the announcement section. Sorry? Yeah, toplets, exactly. That's the term that they use. So if you've never heard that term before, it's, you know, don't worry about it. It's just a term. OK, so a matrix is toplets. The matrix H. Toplets. I assume it's someone's name. I haven't looked up the history of this. Toplets, if hi1j1 is equal to hi2j2 whenever I1 minus j1 equals I2 minus j2. Okay, that's the math statement of the color. So if you're, like, you know, really math inclined and think in terms of symbols, here you go. If you're more pictorial, like most people, like me, just memorize the picture. Is a Toeplitz matrix symmetric? What? No? Is it necessarily symmetric? I can load the question this way. Is a Toeplitz matrix always symmetric? No. Symmetric would require that, like, the blue equals the yellow, right? Symmetric means that you flip it and you get the same thing. So you know, if you had orange and then blue on both sides and then green on both sides, that would be a matrix that's Toeplitz and symmetric. But you can certainly have matrices that are Toeplitz but not symmetric, or symmetric but not Toeplitz. I mean, this is actually a symmetric matrix that's not Toeplitz, right? OK. OK. So that matrix, our H over there, is Toeplitz. So our H, if you just look at the pattern there, you'll see the LK entry of H is the impulse response evaluated at sample L minus K. OK, so therefore it's Toeplitz. OK, so now at least we can sort of describe the problem. OK, so mathematically, we know how to handle circulant matrices very well. We know how to diagonalize them with the DFT. Very clean story. OK, the trouble is the ComCloud server effectively multiplies by a Toeplitz matrix, not a circulant matrix. So our diagonalization result, it might appear, is not very useful. OK, but we'd like to use it nonetheless. And so what we're going to do is try to kind of paper over the difference. OK, sort of like fudge the difference between Toeplitz and circulant. So I'll show you a few ways of doing this. This is methods for making Toeplitz matrices. I'm going to try to say this precisely. Look circulant. It's intentionally a kind of vague heading. So these are just tricks basically that allow you to apply our result for circulant matrices to a Toeplitz matrix. Okay? This is not an exhaustive list, by the way. Okay, I'll show you 3 methods that allow you to bridge the gap between circulant and Toeplitz. It's definitely not exhaustive. Okay, there are other ones. I think there's going to be one on the future homework set. You can maybe invent your own, actually, if you just kind of stare at this for a while. Maybe invent some other trick for bridging the gap. Okay, so it's not exhaustive, but it does show you kind of the spectrum of a spectrum of solutions. So first, let's look at a small version of this where we can draw the whole matrix without the ellipses. Okay, so consider like a 4x4 version of this with maybe n minus and n plus both being 1. So the 4x4 version with n minus and n plus both being 1 would look like this, right? First row would be h0, h1, 0, 0. We have h0, h minus 1, h plus 1, 0. 0, h minus 1, h0, h1, and then 0, 0, h minus 1, h0. Right? Okay, I just took that general matrix there, okay, and I did the 4x4 case where n minus and n plus are both 1. So it stops at h1 and stops at h minus 1. Yeah? Yeah?
So why is positive 1?
Sorry. Okay, that's why people are staring at me funny. Yeah. Yeah, for some reason it always feels backwards from what it should be to me anyway. Good. Minus, 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 like that. So I had the minus wrong and the plus 1 wrong here. So it's minus 1 on the super diagonal, 1 on the subdiagonal. Yeah. That's a Toeplitz matrix, right? It's not a circulant matrix, right? To be circulant, each column would have to be a rotation of the one before it, right? And this column is not a rotation of this one unless h of minus 1 happens to be 0, right? So it's not circulant. Let me pose a question to you. What's like a minimal change I could make to this matrix that would make it circulant? So describe to me another matrix that's not equal to this one that's circulant and that involves like changing the minimum number of entries. What would I do? Yeah?
Throw h of minus 1 at the bottom left. Oh yeah, top right, you gotta add.
And?
The top right corner, the 1.
Is that circulant? Yeah, right? So take the left column and then start rotating downward. So first downward rotation gives me this, downward rotation gives me this, downward rotation, circular rotation gives me that. Right? So that is a circulant matrix. I'm going to call the yellow one C. Okay? And we're basically going to be interested in situations where H, the original matrix in white, that has the 0 here. Maybe I should put a 0 in parentheses. 0. So H has a 0 there, and C has a H1, H minus 1 there. Okay, so I have two matrices drawn at the same time here. Okay? So I'm going to describe situations in which H and C sort of behave like the same matrix for our purposes. Okay? By the way, I can define, whenever I have an H in this form here, okay, I can always define a C derived from H by just taking the missing entries and just putting them where they belong down here. Okay, so I illustrated that in the 4x4 case because it's easiest to see there. Okay, but this will always work, right? I mean, given an H matrix with this banded structure to it, okay, I can always form a circulant matrix by just taking the entries that effectively fell off the end of the matrix and just copying them on the bottom, and likewise on the top up here, okay? All right. So when does H behave like C? So here's some situations where that's true. So suppose you're considering a matrix product like this, H times X. Okay, I claim it's the same thing as C times X if X has appropriate zero padding. So if xk is equal to 0, for k in the range 0 up to n minus 1, or k between n minus n plus and n minus 1. Okay, so the way to see that is as follows. So here's my H. It's got these like non-zero values in this band, right? I multiply that by X. This is X. Okay, C I get by taking H and forcing it to be circulant by copying the missing values in place of the zeros. Okay, so there it only took one entry on each corner. In general, you're going to have n minus, like a triangle here of n minus by n minus symbols. And you're going to have a triangle up here with n plus by n plus symbols. Okay? All right, now observe, here's my X. Suppose X has got zeros in the front and back. Suppose it has n minus zeros in the beginning and n plus zeros at the end. If you can read that. Let me write this more clearly. So n plus zeros there, n minus zeros here. Like that. You see what happens? So when I go to multiply this, any given row, right? The first few rows, the first few columns of H get multiplied by zeros here up until you reach this point, and then you're multiplying as usual. And then when you get to this column, you're multiplying zeros in X, right? So what H has kind of to the right of that line and to the left of that line doesn't matter because it's always going to multiply by 0 in the X, right? I'm just thinking about taking the matrix multiplication amounts to taking, a coefficient here, multiplying it by a column there, a coefficient here, multiplied by a column there, and then add, right? So the coefficients for all of these columns are 0, all of these columns are 0. So it doesn't matter whether you got the yellow there or not. It's going to get multiplied by 0 anyway, right? So if this is the matrix multiplication you've got, you can just pretend it's that because you get the same answer, right? And if that's your matrix multiplication, then you can apply our results for circulant matrices because you effectively have a circulant matrix, right? So it's like the distinction between tulplets and circulant actually doesn't even arise if X has appropriate zeros. Okay, so that's one way of bridging the gap. Just always ensure that when you're doing a matrix multiplication, always ensure the input to your system has got zeros on the front end and back end. And sometimes you can do that, sometimes you can't. I mean, sometimes you want to send a pure tone through the system, through your channel. So if you take a pure tone and then start tacking zeros on the front end, front and back, it's not a pure tone anymore, right? So you've kind of destroyed the purity of the tone by doing that. If you're trying to send an impulse, okay, then putting more zeros on the front and back doesn't really hurt anything. But if you're trying to send a pure tone, then this pollutes it. Okay, so that sometimes works, not always. Second method, take n to be really, really big. Much bigger than the duration of the impulse response. I'll put +1 here maybe, so it's exactly the duration of the impulse response. Just take the time horizon, the duration of all of these signals, x and y, to be really, really big. In that case, hx is approximately cx. It's not going to be exact. And even this, I can't even say this really for all x. It's like for most x in some sense. I'm going to be really kind of cagey here for most x. Okay. You see why? Why would this be true? N's really, really big. So what's the dimension of h? Is n by n, right? And I'm keeping these fixed. The width of this band is governed by n plus and n minus, right? So if n's really, really big, and n minus and n plus are fixed, then this matrix multiplication, pictorially, looks like this. Okay, I can't really draw straight. That's supposed to be straight. Here's the diagonal. Okay, and then my little addendum here to make it circulate. Like that. See what I'm getting at? It's like whether these are here, these yellow parts are here or not, like almost doesn't really matter because there's such a small fraction of the overall matrix that like it doesn't really make much difference whether you put them there or not. And I say most because obviously, I mean, if your x is like an impulse, if your x is 1 and then a bunch of zeros, you're picking off the first column. So yeah, then the first column will either have zeros toward the end or not, depending on whether this thing is there or not. So it's not true for like literally every x. But if you put a pure tone in here, okay, and pass it through, whether you have the yellow part there or not, it's not really going to affect the multiplication very much. Okay. That's another way of fudging the difference between regular convolution and circular convolution. Just make the time horizon be really big, okay? And then like the usual thing, the edge effects that arise from the finite length just sort of become less and less significant in the large time horizon limit, okay? All right, let's take stock of one thing here before I show you the third method. So you probably learned hopefully you learned in your signals and systems class that the Fourier transform turns convolution, that's regular convolution, into multiplication, right? That's like the mantra of 2200, right? Fourier transform turns convolution into multiplication. Okay, now here comes Professor Wagner and he says, no. The Fourier transform, i.e. the DFT, turns circular convolution into multiplication. Regular convolution, not so much. And that's a problem for us. And so we've got to fudge the difference now. How do I reconcile these two statements? Were they pulling like wool over your eyes in 2200? Were they telling you something that was wrong? And now I'm correcting it? Is there an inconsistency there? Yeah, exactly. Okay, so when they say in 2200 the Fourier transform turns regular convolution into multiplication, they're making that assertion over like signals that span the entire time horizon, like doubly infinite signals. Okay, for doubly infinite signals that's true. Okay, it's when you look at like finite duration signals that breaks down. For finite duration signals, it's circular convolution that's converted to multiplication by the Fourier transform, not regular convolution. Okay. In the large time horizon limit, however, here, okay, the distinction between circular convolution and regular convolution vanishes. Okay, and so at that point you just say the Fourier transform turns like all convolution, both forms of convolution, into just multiplication. Okay? So there's really no discrepancy between what they were telling you then and what I'm telling you now. It's just they were only operating in this infinite time horizon limit where the distinction between these two is not so important. Okay, we cannot operate in this regime though. Okay, I'll explain why in the later lectures, why we can't just take n big and then not even worry about this. Okay, but we have to consider the difference between the two. Okay, you've almost certainly used either one or two or both in a prior class, perhaps without even using it. Okay, in particular, like you want to do a lab in 2200. Maybe you don't want to do a lab in 2200, but suppose you're the instructor for 2200. Okay, so you cover the Fourier transform, discrete time Fourier transform. Okay, for doubly infinite signals. Okay, now you cover that in class and you want to assign a lab, okay, where you check that like multiplying in the frequency domain is the same thing as convolving in the time domain. So we're going to do a MATLAB exercise that just verifies that, right? Sounds like a good plan? Okay, now everything in MATLAB is finite time horizon, right? This is a computer. Everything's finite time horizon. Finite time horizon, the DFT does not convert regular convolution into multiplication. It does circular convolution. But you're in a bind here because you haven't covered circular convolution in your class yet. Okay, so what do? So there's a couple of approaches. One is just sort of quietly make sure that every signal that the students put through has got this zero padding. Okay, and then the distinction between circular regular convolution and regular convolution vanishes, and students don't even know what they're missing. Okay, another approach is just make sure the time horizons are really big. Okay, so the distinction between regular convolution and circular convolution again vanishes. And then just like sweep it under the rug that way. Okay, so I bet if you go back to your 2200 labs, if you still have them, okay, this distinction was being swept under the rug, probably either using this or using this. Okay. Okay, any questions on 1 and 2? Okay, so let me show you the third one. So the third one is much more clever than the first two and much more involved, but much more important for us. So the third one is going to form the basis for the systems that we design, the communication systems that we design. So I'll go through it slowly because it's important. And it's a bit hard to digest the first time you see it. Okay, so number 3. So I'll say pre and post pend a cyclic pre and post fix. Okay? So that's the name of it. Okay, so here's how it works. Let's suppose the input that you want to send is x. So here's the wave file I want to send over my channel. x1 through xn minus 1. Okay? So far, so good? Now, I'm not going to quite send x. Okay, I'm going to pre-process it and then send the pre-processed version through the system. Okay? So I'll say, right, let me put it up top because it's important. Don't send x. Send instead, okay, another wave file, another signal, which I'll call maybe x prime. Which I'm going to use a slightly non-standard indexing for. So its first sample will not be indexed with 0. It'll be indexed with minus n minus 1, I guess. No, sorry, just minus and minus. And then it will go up to n plus n plus minus 1. Okay, so I'm not going to send this signal. I'm going to send a different signal that's going to use the following indexing. Okay, and this input is going to be derived from this one. Okay, in the following way. So 0 to n minus 1, I'm just going to copy it over. Okay, so for these samples right here in the middle, like that, just take the x you started with, just populate it. Okay? Okay, here's the key part now. These samples at the beginning, I'm going to derive them by taking the last symbols here and copying them up. Okay, so x n minus 1 is going to get placed here. X n minus 2 will get placed there, up to x n minus n minus, right? So I'm going to copy n minus symbols from the tail end of this vector right here. Okay, and just prepend that to the whole vector. Okay, so it's gotten longer when I do that, okay? Likewise, I take the first n plus samples, the first n plus samples from x, okay, and I append them to the whole vector. So then we get x 0. You can read this x n plus minus 1. So this may be helpful to have partition in your head. So there's kind of an important division there and an important division here. Okay, so x prime consists of x, okay, with some of the tailing symbols, some of the last symbols of x prepended, specifically n minus. The last n minus samples of x get prepended, and the first n plus samples of x get postpended. Okay? So x has gotten longer now. We've added n minus plus n plus symbols to it, or samples to it, right? Okay, so then we send x prime. So let y prime be the output. Okay, so pass x prime through your system, you get a y prime. Note that h is like different dimension from what we might have thought we were starting with, right? And if you pass x through the system, you end up multiplying it by an n by n matrix. Here I'm passing x prime through, so it's an n plus n minus plus n plus by blah blah, yeah, by that. Maybe I should write that here. So this is n plus n minus plus n plus by the same thing. Yeah.
Could you go back one step when you were talking just earlier when you were talking about you took part of it and then you prepended it? Could you mention again what part you prepended and what part you postpended?
Yeah. So this is the input I started with. Okay. Maybe it's helpful to sort of partition it this way. So I can consider the first n plus samples of this, right? This sample is somewhere in there, okay? So kind of draw a line here, okay? And then here's the last sample. And here's some other samples somewhere in the middle, like that. Let me draw a line here, I guess, like that. Okay, so I partition the vector this way. And I'm using the fact that n, I made this mistake last time too. I should have said it just like stated early on that we're assuming n is bigger than n plus plus n minus plus 1. So that the time horizon is bigger than the duration of the impulse response. Okay. If that's true, then like this sample is farther down than that one. So then anyway, I partition this into 3 parts. There's the first n plus samples, there's the last n minus samples, and there's everything in between. Okay. So to form x prime, I take the full x, copy that in the middle. The full x is there. Okay. I take the final third, I mean it's not third, but the final part, this third of the 3 pieces, I prepend that at the beginning, and I take the first n plus samples, and I append that at the end. Yeah.
It's n plus minus 1, right?
N plus minus 1, yeah. Sorry. Let me do it in pink so that we're clear that was a change. N plus minus 1, and then n plus. Yeah. So the first n plus symbols get appended, and the last n minus symbols get prepended. Okay? Is the operation clear? Okay, given any input, I can form an x like this, right? Here. No matter how you populate that, I can populate this way. We then pass this through the system. Does that answer your question?
Yeah.
Okay. So we then pass this through our system. And then I'm going to post-process y now by windowing it. So y is a vector, or y prime is a vector. I can choose to index it however I want. I'm going to choose the same indexing as x prime. So you start with minus n minus, pass through 0, pass through n minus 1, and then up to n plus minus 1. No. Yeah, that's right. Good. Oops. Sorry, my handwriting is. You know, I once had a circuits instructor who, like in the middle of the lecture, he said, "So I'm having a bad handwriting day," and he kept going. I thought, "Oh, isn't that funny? It's like a bad hair day," and it's a thing. I can tell you, it's a thing. Hopefully, you can read this. This is y prime all the way down. Okay, so I choose to index y prime like this. Then you window y prime to get y. We'll use the usual indexing for y. And y is going to be just samples 0 through n minus 1 of y prime. Like that. Okay, so I'm dropping like n minus samples. I'm effectively just dropping all of these samples, and I'm dropping all those samples. Okay? Is the end-to-end operation clear? And each step is not really that complicated, but there's kind of a lot of pieces. So let's just run through it quickly end to end. Okay, you take the input you want to send, partition it like this. Okay, take the last set of samples, prepend a copy of them to the front. You don't move them, okay? You leave them there, but take a copy of them and prepend the copy. Likewise, take the first set of samples, take a copy of it, append the copy. So you have a vector now that's longer. Pass that longer vector through the system. Okay, when it comes out, then cut it down to n samples again by just dropping the n minus samples from the beginning, kind of corresponding to this part here, and drop n plus samples at the end corresponding to that part, and you end up with just n samples in y. All right? So here's the question. How is x, n to n? Here's my input. Let's view all of this as part of the system. View this prepending and postpending as all just part of the system. End to end, how does x give rise to y? How are they related? Okay? That's the question. Okay, so here's the cool part. The output is just x times a circular matrix. With impulse response. C. Okay, which looks like the following. It's got H0 through up to Hn plus at the beginning, and then a bunch of zeros, as many as you need to get it to be n-dimensional. And then you have H of minus n minus, I guess, down to H minus 1. Like that. This is basically the C matrix that we get by taking H and then, forcing it to be circulant by copying the missing values into the corners. Okay, so the theorem is it works, basically. It turns Toeplitz matrix multiplication, it turns regular convolution here into circular convolution, circulant matrix multiplication. Okay, that's the point of the prepending, the postpending, and the windowing. Okay, and we call this part here the cyclic prefix, and we call this bottom part the cyclic postfix. No likey. Did I do this wrong? This could be bad. This could be bad. This is the trouble. So I don't like to lecture from notes because otherwise, I find I'm just going to bury my face and it's not a very interactive. But then, especially when doing this like index intensive stuff, it's easy to get the indices messed up. We need n plus samples at the beginning and n minus at the end. I did this wrong. Sorry. So I'm going to do this in orange so it's clear what the fix is. So I just got n minus and n plus swapped. Okay, so we're going to put we're going to have n plus samples that we append and n minus samples that we postpend. Okay. It's correct that you're taking the bottom part of x and prepending that. It's just a question of how many samples do you do. Okay, so we were doing n minus samples before. It should be n plus samples that you do. And this is supposed to be n minus. So this was supposed to be minus, and this is supposed to be plus, like that. Okay, so here too, I'm sorry, this propagates through, like that. Okay, so it's still true that, like I said, it's still true you're taking the bottom part of x and kind of prepending that, and taking the top part of x and postpending that. It's just a question of how many samples do you do. So I had those mixed up. So you take n plus at the end and prepend that, and take n minus at the beginning and postpend that. Okay? So hopefully I got this right now. Let me do a quick comparison here. Yeah. Let me point out the way I caught this, okay, is I was about to say that, you know, how many samples you prepend and postpend depends on the duration of your impulse response, right? It's governed by n minus and n plus, okay? In particular, if the system is causal, right, then n minus is 0. And so you're not going to postpend anything, and you're only doing the prefix, okay? In practice, that's kind of the common case, okay? So mathematically, you know, you both prepend and postpend. In practice, you typically don't need the postfix because your system's causal, so n minus is 0 and not needed. Okay, that's just like empty, okay? So that's how I caught this, because, you know, with the other indexing, if the system was causal, you'd have the postfix but not the prefix, and I know I just remember that that's wrong, okay? So in practice, you tend to have the prefix, not the postfix, because the system's causal. Okay, but we're looking at the general case right now. Okay. So is the operation clear? We're going to take x, we're going to pre-process it, pass it through the system, post-process by windowing, and the claim is end-to-end. That whole thing behaves like a circular convolution. Okay? All right, I'm going to prove this because it's such an important result for us. It's a bit tedious, but I think, I don't know, it's not good to get in the habit of just kind of taking things on faith. So given how important this is for us, I intend to do it. But once we're done with this proof, we're done with the background section. Okay? All right, so let me note a few things first. So one is, as we noted before, the matrix H at entry LK is just the impulse response evaluated at time L minus K. Okay, 2, if you look at the x prime vector, it's the x vector mod n. Okay, so x prime of L is x of L mod n. That's true for all L valid indices for x prime. So minus n plus to n plus n minus minus 1. Okay, so that, you just stare at this and you see it. So for 0 to n minus 1, that's certainly true, right? 0 mod n is 0, n minus 1 mod n is n minus 1, okay? And then here you're going to have x prime of minus 1. That is indeed x, minus 1 mod n is n minus 1, right? And likewise, minus 2 mod n is n minus 2, and so on. And likewise up here, so x prime of n is indeed x0, which is x n mod n. Okay, so just check kind of all the cases to see that. And then lastly, h of L is c of L mod n for all L in the duration of the impulse response. Okay, so the way to show that, again, you just check it case by case. So if L's positive, 0 up to n plus, okay, then it just follows right from here. So, you know, h0 to hn plus is c0 to cn plus. And then h minus 1 is cn minus 1, which is minus c of minus 1 mod n. And likewise for all these other ones. Okay, so this is kind of even by tedious. Like, it's not really, this is not deep stuff, but you just got to keep track of all these indices, like, which I did not do a very good job of right in here. Okay. So those are our three lemmas, if you will. Okay, so now fix L in 0 to n minus 1 and consider y prime of L. All right, I'm going to use I'm going to index the entries of the matrix H using this system right here. So starting with minus n plus up to n plus n minus minus 1. So the matrix multiplication you write is sum over k from minus n plus up to n plus n minus minus 1. H of Lk, x prime of k, right? That's my matrix multiplication, right? X prime times h gives me y prime. Okay, so there's my matrix multiplication, right? Just sum across the row. All right, I'm going to use 1. This is h of L minus k. All right, let me do a change of variable now. Change of variable. M will let be L minus k. Okay, so just do the change of variable. And what do we get? So M is going to range from what to what? So plug in for k, we'll get L plus n plus, right? And then the lower limit will be L minus n plus n minus minus 1, right? H m x k, which is L minus m. If I have that right, please stop me if I get something wrong, because if we don't catch it for 5 steps, then it creates all kind of havoc. Prime, x prime, right here. Is that okay? Seems all right. Okay. Let's think about these indices, right? So h here is non-zero. Between minus n minus, so minus n minus, and n plus, right? Okay, L is non-negative. It's between 0 and n minus 1. Okay, so L plus n plus is hanging off, it's bigger than n plus, right? So I only need to sum up to n plus here. I can drop the L, okay, because anything beyond that is going to be 0, right? N plus is like the final, the last non-zero sample of the impulse response, right? Okay, likewise, if you look at the lower limit here, L minus n plus n minus minus 1. If we lower bound that, no, sorry, I want to upper bound that. That is upper bounded by, L is upper bounded by n minus 1. Right? So the n's cancel, the minus 1's cancel, and you're left with minus n minus, right? So this lower limit here, right, is only below the left limit. Okay, so I only need to sum down to minus n minus here. Okay, and any additional samples are 0 because we're hanging off the edge of the impulse response. Next, I'll use, which one have we used? We've used 1. I'm going to use 2 right now. So use 2. And you get y prime L equals sum m equals minus n minus up to n plus hm x L minus m mod n. Yeah? I hear whispering. Is there something wrong? Please tell me if there's something wrong. I don't want to wait until things are propagated. Okay, so that uses step 2. I just replace x prime of L minus m with x L minus m mod n. That's the 2 over there. Okay? Almost there. If we now use 3, notice I'm summing over the range for which 3 holds, right? 3 is true over the indices minus n minus up to n plus. So I can plug in for h. And we get c m mod n. Now I've got mods in both of them. X L minus m mod n. Let me leave the notes up. All right, so last step is I'm going to split that sum up. So m running from 0 to n plus. And then the negative terms.
Is that still y prime?
It's still y prime. It's actually this both, but yeah. Yeah, if I just copy it over, it's y prime. You're right. Okay, I just split the sum into 2 parts. We got the positive indices, the ones where m is non-negative, and the ones where m is negative. I just write it as 2 sums. The reason for doing that is when m ranges from 0 to n plus, this mod does nothing, right? Okay, whereas in the second term, I guess I would do, can we bring k back? K was changed, swapped out, right? So let's bring k back. Define k to be n plus m, in which case I get k ranges from n minus to n minus 1. But then the n that I add in gets absorbed in the mod, right? So I don't change this, I don't change this. Yeah, so just do this change of variable, the limits of summation change. These arguments do not change though, because plus n minus n gets absorbed by the mod n, so you don't need to change anything there. Right? And the reason for doing that is that now for k over this range, you don't need the mod anymore. Sorry, I guess you've got to replace k with m. I'm sorry. I mean, you do have to change something. That becomes k. You just change the variable, but you don't have to add anything. You don't have to add, the n in. Okay, now if k ranges over this span from n minus to n minus 1, we don't need the mod here. We're done. We're basically done. So y prime L equals, okay, I can put the two sums together. So there's a lot of erasure going on here. Let me kind of summarize where we are before I do any additional steps. So y prime L equals sum m equals 0 to n plus c of m x L minus m mod n and then we have m ranging from n minus up to n minus 1. Same summand. Okay, so I just put m back in place of k after the just relabel. That way we have the same dummy variable label in both terms. Okay, now Cm equals 0 if m is between n plus 1 up to n minus 1. Okay, that's the way we define C is erased. But if you look at C had a bunch of non-zero values at the beginning, and then a bunch of zeros, and then non-zero values at the end. Okay, so this is the span of the zeros right here. If you go back to the definition of C, okay, you'll see that C vector had zeros all in here. Yeah, go ahead.
In the second summation, isn't it with k now?
Well, no, I put it back to, so we did a change of variable here, and after I've done the variable, just replace k with m so that they have the same variable in both sums. Yeah, because I want to combine the sums, these two sums into one now, so it's helpful to have the same variable here. Yeah. Other questions? Okay, so I'd like to view this as a sum from m equals 0 all the way up to n minus 1, but I've got missing terms, right? We've got 0 up to n plus, then a bunch of stuff missing, and then we've got the end of the sum, right? But the thing is, if you go back and look at the definition of C, C was 0 for all of these terms that are missing. So I can just throw it in for free, because C is 0 for all those terms that we don't have. So you're left with y prime L is sum from m equals 0 all the way up to n minus 1, C m x L minus m mod n. Okay, and this is true for all L between 0 and n minus 1. If you look at the beginning, we assumed L was anywhere in that range. Over this range, L is just defined to be y prime of L. Okay, so you get y, you can then drop the prime right here. And then drop the prime, and you have y equals that. Okay, so finally, y is just the circular convolution of C and x, which we know you can write as the circular matrix C times x. That's it. Okay, so that's the proof. There's, like I said, it's not, each step is not really that complicated or deep, but there's a lot of steps, and many of them are kind of hard to keep track of with all the indices and so on, so you're going to go through it step by step. There's a picture. You can also try to prove this pictorially. It's not really very rigorous, but it's helpful to understand what's going on. It would probably take me like 2 minutes, maybe 90 seconds to do the picture, and we're just out of time now. So maybe on Thursday, should I start with the picture, or should we go right into, or on Tuesday, should I do the picture, or should we go straight into modeling the channel? Picture? Okay, so we didn't quite finish the background in as much as I'll just show you like the picture to have in your head for why this works. I'll do that on Tuesday, and then we're done with background, and we'll start with modeling the channel. All right, I'll see you Tuesday.